This video is at the request of students who want some reinforcement about how hybridization works and how hybridization can lead to the formation of pi bonds and sigma bonds and what the distinction between those bonds is. So let's start with the need for hybridization. We know that carbon has 4 unpaired electrons, but this doesn't match with its electron configuration. So all we can do to get 4 unpaired electrons is to take this paired electron from the 2s subshell and put it into the empty orbital in its 2p subshell, such that carbon now has 4 unpaired electrons. However, we technically can't do this because the Aufbau principle states that in order for us to start adding electrons to a given subshell, every subshell below that, at lower energy levels below that, must be full. So the way that we kind of cheat the Aufbau principle is we hybridize the 2s and 2p subshells together such that all 4 of their orbitals now exist at the same energy level, and this new hybrid subshell is what we call the 2sp3 subshell, because again we're combining the 1 orbital from the 2s subshell and all 3 of the 2p orbitals together, and this allows carbon to make 4 unpaired valence electrons. I haven't bothered redrawing the 1s subshell here because these are the core electrons that aren't affected by hybridization, which strictly affects valence electrons. Now, if we connect this to bonding, let's redraw carbon's valence shell, the 2sp3 hybrid orbitals here. And again, that shows us that carbon has 4 unpaired valence electrons. And in order for us to form a bond, we simply take 1 unpaired electron from one element, like hydrogen, and pair it with an unpaired electron that another element has, such as one of carbon's. And when we take 2 electrons and pair them together like this, as long as one of those unpaired electrons comes from a hybrid orbital, because this is a sp3 hybrid orbital here, this forms what we call a sigma bond. Again, a sigma bond forms when 2 electrons that are originally unpaired from 2 different elements pair together, and when one of those electrons comes from an orbital that exists as a hybrid orbital. For that reason, all 4 of the bonds that are made between carbon and hydrogen in order to give us CH4, methane, are sigma bonds. But when we take a look at different ways that carbon can hybridize, we see that this will not always be true. For example, if we look at how carbon forms double bonds using sp2 hybridization, we can begin at basically the same starting point with carbon's 4 unpaired electrons split across the 2s and 2p subshells. But this time, the hybridization event is different because we're only going to join the 2s subshell with 2 of the 2p orbitals, such that we end up with a hybrid subshell that we call the 2sp2 subshell, because again, 1 orbital from the s subshell and 2 orbitals from the 2p subshell, resulting in carbon having 3 unpaired electrons like this, which means that the remaining p orbital here, this is the last orbital left from carbon's 2p subshell, is not hybridized and remains separately. And this is necessary because of the difference in the way that double bonds form. Now, if we look at how carbon forms a double bond, so the compound that we're looking to make is C2H4, which we know from organic chemistry is ethene, we can, if we draw hydrogen's unpaired electrons in their 1s subshells, and then if we consider carbon's hybrid orbitals in the 2sp2 subshell here, sigma bonding works exactly the same way, where we take 1 electron from hydrogen from its 1s subshell and pair them with each of the unpaired electrons in carbon's 2sp2 hybrid subshell, and the result is the formation of a sigma bond, because once again, the unpaired electron from carbon's 2sp2 subshell is an electron that exists in a hybrid subshell, and we can make 3 of the 4 bonds of each carbon this way. We can form a second carbon to hydrogen bond by taking this hydrogen's unpaired electron and pairing it with the second of carbon's 2sp2 electrons, so there is a second sigma bond. And then the third electron we actually get from the other carbon here. So this carbon is going to donate one of its 2sp2 electrons because it is hybridized in the same way. It's going to take one of its 2sp2 electrons, donate it to this carbon, giving us a carbon-to-carbon single bond, and because not just one but both of these electrons came from a hybridized orbital, this is what we call a sigma bond. So if we draw the Lewis structure of what we just constructed, this carbon-to-carbon single bond is a sigma bond, and each of the bonds between carbon and hydrogen are also sigma bonds. The only bond that we have not yet added in is the double bond. And the reason why that is because that electron comes not from any of the hybrid orbitals that we made, but from carbon's unhybridized 2p orbital that did not get combined with the 2s subshell. And each carbon has one of these unpaired electrons, which means when these 2 electrons pair, they form a pair of electrons, which allows us to make a bond. And when this happens, there are 2 p orbitals, the p orbital on this carbon and the p orbital on this carbon, overlap with one another and give us a bond that has a different structure than the sigma bonds that we constructed. Neither of these 2p orbitals are hybridized. They are specifically unhybridized orbitals, so this is not a sigma bond. This double bond here, for the first time, we are seeing a pi bond because, again, neither of these p orbitals here are hybridized. As expected, triple bonds work exactly the same way, except with slightly different hybridization. So if we start with our 4 unpaired electrons in the orbitals that are unhybridized, now with triple bonds, we are going to have to make 2 pi bonds, which means that the hybridization event that is going to happen is only going to be the s subshell and one of the orbitals in the 2p subshell, such that this hybrid subshell is what we call the 2sp hybrid subshells, and that means that these 2 remaining p orbitals here are not hybridized, which means that we can make not 1 pi bond like we saw with the double bond, but we can actually make 2 pi bonds. So let's look at the Lewis structure to see how this happens. Again, if we start with carbon, specifically looking at its hybrid subshell, the 2sp subshell, we can form sigma bonds exactly the same way. Hydrogen donates its unpaired electron and pairs with the electron in one of carbon's 2sp hybrid subshells, and there is our first sigma bond. And then the second electron pairing that happens is with the other carbon's unpaired electron in its 2sp subshell, such that we get another pair there, and that results in a carbon-to-carbon single bond. So if we compare this on the Lewis structure, the only bonds that we have made are the single bonds between each carbon and its hydrogen, and the single bond between each carbon. However, as we know from the hybridization, each carbon has not 1, but 2 unpaired electrons in, again, not 1, but 2 unhybridized 2p orbitals here, which means that these 2p electrons can pair together in order to give us a double bond, and then the second pair can pair together in order to give us a triple bond. So again, both the double bond and the triple bond are considered pi bonds because neither of the unpaired electrons that made the bond came from a hybridized orbital. Both of these came from the unhybridized p orbitals that both carbons have. And this is why double bonds and triple bonds exist as pi bonds, but single bonds exist as sigma bonds, because at least one of the unpaired electrons that made up the bond came from a hybridized orbital. The final topic in the video is to explain how sigma bonds form with elements that have expanded valence shells. So if we consider phosphorus and sulfur, the mechanism works fairly similarly. If we consider the electron configuration of sulfur, it would be neon 3s2, 3p5. We know that phosphorus begins with 5 valence electrons, and one of them is normally a lone pair. However, again, this doesn't explain how phosphorus is able to make 5 bonds unless we take one of its electrons in its 3s subshell such that it is no longer paired and jump that electron up to an empty orbital in its 3d subshell. However, again, we need to reconcile with the Aufbau principle because normally we can't fill the 3d subshell unless every orbital below it is already full. So again, we do a hybridization event where we don't just hybridize the 3s and all of the 3 orbitals in its 3p subshell, but we also join to it this one orbital in the d subshell, such that this hybrid subshell contains 5 orbitals that are all at the same energy level, thereby allowing phosphorus to have 5 unpaired electrons. Now, if we look at the formation of the compound PCl5, phosphorus pentachloride, we know that chlorine has 1 unpaired electron in its 3p subshell, which it can join with one of the unpaired electrons in phosphorus's hybrid orbitals that we've constructed here. I'm just going to redraw those to make this pairing more explicit. So, chlorine can take its unpaired electron in its 3p subshell and form a bonding pair with one of the unpaired electrons in phosphorus's hybrid 3spd or sp3d subshell. And right there is a bonding pair. And again, when this electron pairs with one of phosphorus's electrons, that results in a sigma bond being formed because phosphorus's unpaired electron came from a hybrid orbital here. If we look at how sigma bonds form in sulfur compounds, it's very similar. So if we consider the electron configuration of sulfur, we would start with 3s2, 3p4, such that sulfur has 2 lone pairs already. Again, this doesn't explain how it makes 6 bonds unless we take the paired electrons from its first 2 orbitals and jump them up to 2 empty orbitals in its 3d subshell. Then we need to hybridize so that we don't break the Aufbau principle, so we allow all of these electrons to effectively exist at the same energy level, for which we call the 3sp3d2 subshell, because again, we're combining the 3s orbital, all 3 of its 3p orbitals, and 2 orbitals from its 3d subshell, and this allows all 6 of its valence electrons to exist at the same energy level without violating the Aufbau principle. So if we redraw these here to show how bonding would work in a sulfur compound that has 6 bonds, we can see this in SF6, sulfur hexafluoride. We know that fluorine has 1 unpaired electron in its 2p subshell, which it can use to pair with one of sulfur's unpaired electrons in its 3sp3d2 hybrid subshell here. And when that electron pairs, that gives us yet another sigma bond, because again, this is a pair of electrons where at least one of the electrons came from a hybrid subshell, which therefore means that it is a sigma bond rather than a pi bond. So that concludes this summary of hybridization and the distinction between sigma bonds and pi bonds.